The other type of interpolation we're going to talk about is spline interpolation. And to show spline interpolation, I've plotted out a few functions, and I'd like to contrast it with with polynomial interpolation, which we've just covered. Now, just graphically here, we have this original function. So I just have this function it's good for demonstrating, but suppose the original function looks something like this, and we want to fit that data with a polynomial. Well, if we fit it with a polynomial, this is what we get right here. That is what we get. And if the original data was right here, like I said, that is not exactly what we were looking for, is it? It sort of goes all over the place. Now, a linear spline simply takes and has a straight line segment between every set of points. So straight line here, straight line between here and here, straight line between here and here, straight line between here and here, and so forth. And actually, this looks pretty good. It's not that bad. Here's a cubic spline. It's just a higher order spline, and it also goes through the points, and it sort of has this curve shape at the end point. And we'll see more the advantage of a linear versus cubic, but we can clearly see from this information that based on the data given, the splines have a much better fit than the polynomials. And in particular, we call this problem overfitting. Okay, and I'd also like to note here that a linear regression line wouldn't be any good either, right? Because we're not trying to do regression. We don't have just linear. We have maybe sort of this piecewise linear, but that's why the spline makes sense. Okay, so again, regression doesn't work, polynomial interpolation doesn't work, but splines do the job quite nicely. Now, we're going to get into splines a little bit more, but I wanted to show off a little bit what they can do. So first we have this original function, and the original function I'm just using as an example function. I'm just using the sine of x. Okay, so that's all this function is, and you can see it's nice and smooth, just as you'd expect. And we sample it here at these red points. So we're going to evaluate it at these red points, and we're going to go ahead and call those points. We're going to call this one x naught, right? We'll call this one x1. We'll call this one x2. We'll call this one x3, and so forth. x4, x5, and x6. So you see what we're doing there. And those are labeled. They're all the same points all the way through. And then we have this linear spline. So the linear spline, we just draw a straight line between all the points and connect the dots. And you can see that given that the original function was nice and smooth, we have this linear spline, and it doesn't fit that bad. Like it's not that bad, but it could certainly be better. And so that's where we could fit a higher order spline, a quadratic spline, and that's what we get here. And this actually looks quite nice. If you look closely here, it looks really nice. So that's just just the advantage then of a quadratic spline over a linear spline. Now let's look into a little more what it takes to make a linear spline. Well, to make a linear spline, it's simple. It's just between x0 and x1, we do linear interpolation, right? So we'll have f of x equals some, so we'll have some function, and it'll be piecewise. So we can write that. So we say f of x equals, and let's just call it f of x naught plus m, where m is a slope variable here, m naught x minus x naught. Okay, so that works fine, and then that's going to be between, that's good for x naught x1, right? And then we could do the same thing between the next interval f of x equals f of x1 plus m1 x minus x1 between x1 x and x2. So we can do it that way, and we can go all the way down to xn. So this is just all the same f of x, but f xn plus, you get the idea, and you see it graphically here. Well, we do the same thing with the quadratic spline, except we have to do some other special things. So you can't fit a quadratic to these 3 points and then have another quadratic fit to these 3 points. It doesn't quite work right. And so what you do is, well, first let's get some terminology down. The points at which they meet, and so that is called a knot. Okay, so that's the terminology that we use. So where you have like 2 of these line segments meet, 2 of these, in this case linear, but in the quadratic case, if we have where we have 2 of the quadratic line segments meeting, that's also a knot. And in particular, the knots on the inside, these are called interior knots. These are interior knots because they're inside, and then you have the endpoints. Okay, and so this is what we have. Now, if you'll notice here, the first derivative is not continuous at the knots. Okay, so this is a problem. It's not smooth, right? The first derivative is not continuous. In fact, it's not even defined. At the knots, the first derivative is not even defined. What is the first derivative there? I mean, it starts going that way and then it just jumps, right? So it's discontinuous. Well, the quadratic spline fixes that problem, and so we'll have one line segment here, and we do the same thing that we did before. We're going to fit a function, but we're going to fit a quadratic function, and it's going to be a1x squared plus b1x plus c1, right, for here. And then for this one, we're going to call that, here, let me go down a bit. Here we're going to call that a2x squared plus b2x plus c2, right? And similarly, we could have a3x squared plus b3x plus c3, and so forth. So here we have segment 1, this is segment 1 here, this is segment 2 or interval 2, interval 3, and so forth. And to figure out these coefficients, the whole problem then of the quadratic spline is we'll just have to set up a matrix. With a linear one, we could do each one separately, right? One segment didn't depend on the other segment, but for the quadratic spline, we introduced this condition that the first derivative has to be equal. So we set up all these equations so we can write out all those equations. So just like we wrote out all these equations, we can write out all these equations. So we have a1. Let me write these in. Okay, so I wrote out the equations here, and this is just the exact same thing as we had up here, except we've got quadratics instead of regular line segments. And this time it gets a little bit more complicated. So I'm gonna scroll down here a little bit. This time it gets a little bit more complicated. So we have this, but that's not enough information to solve it, right? These are just a set of equations, and we have way too many unknowns. And so the first thing that we're going to notice is, so we have those relationships. the first, so we're just going to add conditions here. So we'll say 1, the function values must be equal. So function values equal at interior knots. In other words, this line and this line, both of these curves, they share that point, okay? That's all we're saying is they share that point. Well, it turns out that gives us 2 more equations. Okay, so and the 2 equations it gives us, I'm not going to write them out here. Maybe I can, but I don't want to take up too much time here. But basically, you plug in this point, you plug into the first equation, and you plug in the second point, you can plug that into the next equation, and so forth. So it depends on how many line segments we have, but we're going to get more equations that way. The second thing that we're going to have to do is we're going to say that the first and the last functions, so first and last functions pass through the endpoints. And that's kind of obvious. Okay, all we're saying is that it has to run through that point here and it has to run through that point here. If it's not, it doesn't work. Okay, next thing, number 3. Okay, so now we got the function values are equal at interior knots, but not only the function values are equal, we have the derivatives are equal, the first derivatives equal at interior knots. Okay, and then we have the fourth condition, number 4. We just need another condition, and the easy one that they use in the book is that they set the second derivative equal to 0 at the first point. So f double prime evaluated at x naught, well, the second derivative of the first function. So the second derivative of this function is equal to 0. That's all they do. So what all this is going to be is saying that this first coefficient is going to be set equal, well, not the first coefficient, but it'll be the a1 will be set equal to 0. So yeah, a1 equals 0. So that's going to wipe it out. It's actually going to make it linear at the first point. And we could do something different. That's not the condition that we have to do, but for it to be a quadratic spline. But that's the easiest one to use to constrain it. And then I'm not going to show the rest of it, but it goes ahead and it goes through the rest of the derivation for this in the book. And all we do is, now that we've got the same number of equations as unknowns, we just represent this as a matrix. And once it's represented as a matrix, we just solve that matrix, and we solve it for all of our unknown values. We get our values, and then we have this piecewise defined function, which is smooth, that goes through all the points that we want it to, and it's really nice. A cubic spline is the same thing, only instead of just having a first derivatives equal and all the, the equal at the points and first derivatives equal, it also constrains the second derivative to be equal at the interior knots. And so that's the idea. And the nice thing about that is, just point out here that the cubic case is nicer. It's a little smoother, and that's sort of the default that everybody loves to go to. And the nice thing about the cubic case is not only the first derivative, but also the second derivatives are smooth, and so it's just a nice smoother thing, and but it still avoids overfitting the data.